Welcome. Post-test day. The room is very empty in comparison. Way more elbow room and all that. But glad to see you all here. So, a few logistics things. I don't know which I should say first because I don't know if it affects things. So I just sent out an announcement, and you might already know this. The student reception of instruction just got sent out. That's the thing where you get feedback on your instructors and all that. Please do fill that out. I put in the announcement. It does not affect your grade in any way. It's completely anonymous, so I have no idea if you filled it out. And I don't. If you say anything like anything, I don't know, bold, we'll say. Again, I won't have it tied to you whatsoever. I won't even see the responses until after all the grades are in. That's when I see them, is after all the grades are in. So there's no possible effect it can have on you in this course, both good or bad. Full clarity there. However, it is very, very beneficial for me to have that feedback, just like from test one. Remember, the feedback helps me. It helps me improve. It helps me identify what is good, what I should keep doing, and identify what is bad, and what I should stop doing. So please fill that out. It means a lot to me. Helps me out in terms of just improving. All right. Speaking of feedback, test 2 scores. All your scores are up to date. All the scores in eCampus are up to date at this point. The clicker questions have been adjusted and updated. The quiz questions except the slash quiz, is also up to date. So those are all graded out of 4.5 instead out of 5. Your recitations and all that, I went in and assigned zeros if you were not there, so I forgot to do the assignments. That might have dropped things. But all those are up to date. Your grade at this point is accurate to what your grade is in the class. What it tells you on eCampus is your current grade in this class, with a couple caveats. One of those caveats is that, remember, I calculate your grades with and without clicker questions. So the fact that you're here in class probably means that you do the clicker questions and you're getting those points, and it does benefit you. But for those that didn't show up to class and all that jazz, at the end of the semester, I would calculate grades with and without clickers and take the higher of the two, but I will not do that until that point. So if you fall into the category of like, I haven't done any of them, your grade might be higher than it currently shows. Currently, the clickers are included in your grade, and that's that. Another thing I want to point out, and this is true of all your classes, I had one student email me asking about their test grade, and there was a mistake in the test grade I uploaded for that one student. Because they notified me, I checked it, saw it, fixed it, double-checked the rest, everything else seemed fine. Everyone else's grade seemed good. I saw why it was in it. So the way I do it is I download the file with the zip. I scan all your old tests, and then I match your student ID to your ID in the system, and somehow, some way, the matching thing that I used wasn't being applied to this one student. But I mentioned this. Remember I told you all mistakes happen? If at any point in my class you think there's a mistake in the grade, let me know. I am more than happy to double check it for you. And then I can check that. And that is true of all your classes. All your classes, if you believe there's a mistake, reach out to your instructor. Always, of course, do it in a respectful way. Don't be like, oh, you definitely made it I don't care how you kind of email carousel level, but do it in a respectful way. It costs you very little, and you gain a lot from it. Just say, hey, I'm curious about this. I feel like you could say, I felt like it did really good. This is lower. Whatever. They can double check. Can I do the test? All that kind of stuff. It could happen to you. 1 out of 293 students. The odds are low, like in this case, but it's just one of those. You have many classes ahead. Your instructors are all humans like myself. So I wanted to use this example of my mistake to notify you it can happen in your other classes. To that end, I will, before final grades are posted, so once we do the final exam, hopefully the day after that, maybe 2 days after it, I will give you all time to review the final grade in this class before it gets submitted to UCF. Because of that. So I will do all the edits, all the changes, all the things that I do, lowest test grade drop, all that nonsense. And then I will notify you all the grade in Canvas is the grade you're going to get in my class. At that point, you can contact me before this if you want. At that point, you'll be able to contact me if you think there's an error. If you contact me and say my grade is this, can you increase it by X number of points? Is there anything I can do? The answer will be no. At that point, I will not change the grade unless there's an error, but I purposefully update the grades and let you see them at the final. After the final, and I notify you and all that, because it is always possible to make mistakes, and so it's best. Who's the best person to check if there's a mistake? The person who's most affected by it. You all. Again, in a perfect world, I'd be perfect, but I'm not. And so anyway, I do that. Last semester, I don't think I had any errors, but it's just one of those last chance for you to make certain everything is what it should be. So, anyway, future thing. Want to mention it. Any questions about any grade stuff? Yeah. Yeah, so the question was, does the final exam grade average out with the lowest? It does not. It will replace the lowest if it's higher. It will just replace it. So, say you get a 40 on the first test, a 60 on the second test, and a 50 on the final. Oh, 40, 60 done. The 50 on the final will replace the 40. It will do double duty. It will be your final exam score and your test one score. So it will count double, but it will increase your grade. Well, unless your finals... Yeah, I guess there's a chance you could still lower it. But anyway. All right. Any other questions? Cool. All right. We have exactly 4 classes left. Exactly 4 classes in this class. Today, Tuesday, Thursday, then Tuesday, and that's it. So exactly 4 classes. I plan on covering new content on 3 of those. And then the Tuesday of Thanksgiving week will be a review day of kind of all the things. All right? My goal is to get through the rotational variables, torque, and moment of inertia. Those are the 3 things I plan on trying to get through. Ideally, I'll also mention rotational kinetic energy. That's really easy to show you all. I have to do, it is mission critical that I get through torque and moment of inertia, because if y'all take statics, half the class is about torque and moment of inertia. So I need to teach you all that. So we will do what I can. I may move a little quicker than I normally do. I may talk a little quicker. We lost a week and a half, y'all. I have half as many days to cover the same amount of stuff. Now, that doesn't mean I'm going to go crazy fast. It actually means I had to cut conservation of angular momentum. But it does mean you might see me skip through some problems or say, here's the answer, kind of try it on your own, that kind of thing. That might happen. All right, last thing I want to show you all. Boop. This is the distribution of test 1 grades. They were the average was a 76, which for a physics class is quite good. You'll find in your future classes that averages tend to be around 60s, and I don't say that to kind of pat myself on the back. I say that as 1, I'm very happy with how people did. 2, this test, in my opinion, is easier than the first test for a variety of reasons. 1 being you're better at physics. 2 being energy and conservation of energy is easier. 3, I did actually make this test a little bit easier for time-wise. Anyway, there it is. There's a lot, these ones over here on the left, or your right, those are all hundreds. That's not a 95. That's how many people got every single question right. It's about 30 people. So that's great. I'm really, really happy. So anywho, just showing you all this. At this point, it's just kind of for your information. Gives you a sense of how you did compared to other people. I mentioned this before. It's not a fun thing to realize, but the reality of life, and again, this has just been my personal experience. Almost everything in life, how you're going to do is going to be how you do compared to other people. It sounds really rough, but a really easy example of this is who gets the job. When you apply for a job, how do they decide who gets the job? They compare you to all the other resumes. When you're in a job, they decide who's going to get laid off. They're comparing you to all the other people. The reality is some of the best metrics for how you're doing are how you're doing compared to other people. And I say that not to say that if you're below the average, that you're a below average individual. That does not mean you're a below average individual. It just means in this specific area, you performed lower than the average. It does not say about anything you as a person. All of you have equal value in work, but it does mean within this context that you perform lower than the average. And then that just, okay, what do we do with that? Okay, so it's an important thing to kind of note. Same thing, if you did better than the average, it doesn't mean you're a better person than other people. It just means you did better than the average person on the test. That's all it says. And you might understand the content better than the average person. Does not make you a better person at all. The value of a human being is not dependent upon how much Physics 1 knowledge you have. Great. All right. Soapbox. Done. As always, if you have questions, you can chat, email me, all those things. My office hours up until Monday, my office hours are used for makeups. Tuesday, my office hours will start back normally. So if you want to stop by, Tuesday and after is good. Fixed axis rotation. This is what we're going to cover. It sounds really fancy. Fixed means not moving. Axis is what it rotates around. It says rotational. We're going to talk about things that rotate about the same axis. So my water bottle, if I kind of spin it in place, this is fixed axis rotation. What does it look like if it's not fixed? If it's both spinning in all sorts of crazy nonsensical directions, we're not going to do crazy spinning motion. We're going to do nice, simple spinning about a fixed axis. Yes, the thing can move left and right. That's fine. It's still spinning about the same axis. We are not going to do crazy rotational nonsense where it's doing crazy things. All right? Now, the major point I want you all to recognize, 75% of what I'm going to teach you all, you can connect to something I've already taught you. So I'm actually going to point that out now, because if you get that, this is going to be super easy. Every variable I've taught you with x, we're basically going to replace with theta. Every equation I've given you that had v, we're going to replace with omega. Every kind of equation we have that has a, we're going to replace with alpha. Theta is the angle. It's kind of like where you're located, but for spinning. Omega is called angular velocity. It's how much your velocity is for your angle. How much your angle changes with time. It's like velocity, how much your position changes with time. So over here, this is meters. This is degrees or radians. This is meters per second. This is radians per second. This is meters per second squared. This is radians per second squared. Every single equation that basically had x, v, and a, so i.e. all the kinematics equations, I'm actually going to jump forward a bajillion slides to show you this, and then we'll get to it eventually, but I'm just going to jump super quick. What I really want to sell to you is that the rotation, the stuff I'm teaching you, 75% of it, if you can connect it, you've already kind of learned it in some way. So you'll see what I mean. I'll keep repeating that. Everywhere force shows up, we're going to replace it with torque. Torque is the rotational equivalent to force. Everywhere mass shows up, we're going to replace it with something called moment of inertia. Moment of inertia is mass, but for a spinning object. It's how mass is distributed. And I think there's one more. We're not actually going to get to this. Everywhere momentum shows up, you replace it with L. It's called angular momentum. So, you may be like, what the heck is he saying? I am mentioning this now, and I'm going to show you some examples immediately. But I'm going to sound like a broken record with this. If you just recognize that rotation is just linear motion, like rotation and linear motion, the equations are identical. It's just a different paint job. So let me show you what I mean. Let me jump to a slide that kind of exemplifies this and shows you what the heck I'm saying. So scroll. Don't worry, we're going to get to all this nonsense. There it is. And actually, I've realized, we'll get to that. Look, you know the answer to one of the questions. I need to delete all the ink on this PowerPoint so I can re-ink it. All right, it's gone. Okay, so where's that slide? You can't see anything. That's wonderful. Boop. All right, here's the one I wanted to point out to you. The left side is equations that you hopefully are very familiar with at this point. If not, You want to make sure you're really familiar with them. They're kinematics equations. VF equals V naught plus AT. Average velocity, you average it divided by 2. X final equals X initial plus V times T plus 1/2 AT squared. Classics, right? Like, again, hopefully you all aren't disgusted by these like you were 2 weeks into class. If you remember way back when. Now, look at the right side. Everywhere that there's a velocity, we just replace it with this is called omega. We're going to learn what it is in class today. All the equations are the same. Everywhere there's a V, replace with a W. Everywhere that there's an X, replace with a theta. And everywhere that there's an A, replace with an alpha. I'm going to teach you all what these variables are today, but I just want to show you all this is probably the most useful thing as the next 3 days when I teach you this stuff. If you're good with kinematics, you're going to be good with, we can just call it rotational kinematics. It's the exact same thing, except instead of X, it's an angle. Instead of velocity, it's angular velocity. But the equations get used identically. The equations are identical, and that's going to be a theme. We're going to continue to see that with every equation I teach you with rotation. Another example will be eventually, F equals ma. Hopefully you're like, yeah, I know that equation. We're going to learn in rotation, it's torque equals I alpha. Torque is like force, M is like I, and A is like alpha. And you use it the exact same way. So we'll get to that when we get to that. But that's really what if you can make that connection, really good learning is all about taking something new and connecting it to something you understand. That's how you make it easier to remember. That's just how memory works. If you can take something new and connect it to something you already understand, your brain remembers things better. There's whole psychology. It makes sense, right? Neurons and all that jazz. They'll learn about that in your psychology class. But anywho, so I mentioned that to you because I want you all to learn it well, and this is how you're going to learn it well. If you just realize it's what I've already taught you with a new paint job. So, case in point. All right, we're going to talk about rotational variables. There's some easy relationships to convert from translational to rotational. Literally just multiply by R. That's it. And then, we're going to go through the various ones, and then we're going to talk about torque. We almost definitely won't get to torque today, but hopefully we can get through all the rotational kinematics today. The next class, I'll teach you all about torque a little bit and hopefully get into moment of inertia. And then if I can do all that, I'm a happy camper. Okay. Fixed axis rotation. Brady mentioned this. It's rotation about a fixed axis. Sounds really fancy, but the words just tell you what it is. So there's our analogy. Arc length is like angle. Or arc length here is our displacement angular. Yeah. I don't know why it says arc length. It should be theta. Anyway, I'll fix that later. But the rest of these are good. Angular velocity to velocity, angular acceleration to acceleration. Let's just jump to this and then I'll fix that arc length thing a bit. There you go, arc length. You've already seen this slide. Hopefully. I'm fairly confident I've already showed you all this. Arc length is the length of an arc on a circle. You just multiply r times theta. If you want to get how far you travel, the distance traveled on the outside of a circle, you just multiply r times theta. Theta is in radians. That is very, very important. If you use degrees, doesn't work. Doesn't work. And if you multiply r times 30 degrees, it gets you an answer that's absolutely useless. And if you remember when I taught you this for the first time, you know this. How do you get the circumference of a circle? 2 pi r. 2 pi is the radians, the angle for an entire circle. So, you've been using this for an entire circle. I'm now teaching you how to do it for a piece of a circle. And this is going to be a very common trend. How do you go from angular to translational? Multiply it by r. How do you go from angle to how far you've traveled? Multiply it by r. How do you go from angular velocity to velocity? Multiply it by r. How do you go from angular acceleration to acceleration? Multiply it by r. It's really nice. It's really simple. All right. And practice. When I say practice, I got to open the clicker. A piece of gum stuck to a wheel with radius 0.5 meters travels a quarter of a revolution. What distance did the gum travel? Oop. You will see the screenshot. I'm kind of displaying things a little different than usual. So you'll see the screenshot looks all crazy. It's the presenter view on my computer. But you can still see the question. Go to the gum travel 0.5 meters, 0.5 pi meters, 0.25 pi meters, or 22.5 meters. All right, we'll go 25 more seconds. In 5, 4, 3, 2, 1. All right. So we're trying to figure out the arc length. It's r times theta. What's r? 0.5. What's theta? It's pi over 2. It's a quarter of a circle. Quarter of a circle, knowing your unit circle is a very useful thing for you all. You don't need to have the unit circle memorized, but man, if you do, it makes your life way easier. You're going to be working with it a lot. So you get pi over 10, which is 0.1 pi, which, nope, made a mistake. Foreshadowing. We get 0.5 divided by 2 is 0.25 pi. There you go. Boop, boop, boop. All right. Quick check for you all. How do I go from distance to velocity? What do I do to, if say I have a function for position, how do I go from position to velocity? You take the derivative. So this is just a quick derivation for the next slide. So if I want, so in this case, we could basically think of s like my x. How do I go from position? I take the derivative and that gives me velocity. Well, great. Do that to both sides. So if I take the derivative of r theta, I get r d theta dt, i.e., the velocity equals r times omega. Omega is that thing I just said. Omega here is the Greek letter, and it is literally just the change in angle divided by time. Angular velocity, it's velocity for angles. How much does my angle change every second? Now the unit for this is funky. Well, the symbol's funky and the unit's funky. So this is not a W. If you write it as a W, that's fine. They look basically the same. This is the lowercase Greek letter omega. It's always good to learn a little bit of Greek. Remember, if you've ever heard the phrase alpha and omega, beginning and the end, omega is the last letter of the Greek alphabet. That's where it comes from. This is the lowercase version of that. So, the weird thing with this omega, remember, it's the angle per second. Angle is measured in radians. Radians is technically not a unit. When you report this, you don't actually say, if I want to say, what's the angle? 30 radians. Radians isn't like a unit. It's not like meters or seconds or newtons or joules. It's like a fake unit in some ways, and it's kind of weird, and there's reasons for that. But the reason I mention this is the units for omega. You could write radians per second. That's fine. I'm not going to knock you off on that. I think it's actually more clear. But you'll often just see the units for this as seconds inverse, i.e., so radians per second. Remember, radians isn't kind of a real unit. These two things are the same thing. As weird as this seems, because radians isn't like a real unit. It's not like meters or seconds or newtons or joules. It's like counts. If I just said, how many cats do you have? 5 cats. Cats isn't a unit. If I told you I had units of cats, you'd be like, what? Radians is kind of like a count. It's not a real unit. So to that end, both of these are acceptable. And what I also want to point out, so this V equals R omega, remember the trend. How do you go from angle to position? Multiply it by R. How do you go from angular velocity to velocity? Multiply it by R. And the reason for that is what I mentioned before. Remember, velocity is dx dt. Omega is just d theta dt. And, why is that meaningful? Remember, x is r times theta. So if you take the time derivative of theta, of that original equation, you get this. There's a nicer slide that walks through that, but I'm just mentioning it now. So there you go. Nice and straightforward. How much does my angle change every second? If I have an angular velocity of 3, that means I get 3 radians every second. Whatever the heck 3 is. Or let's say my angular velocity is pi seconds inverse. That means every second I go half a circle. So, okay, do I want to do this question yet? I'm going to come back to this question. I'm not going to be super mean. I'll teach you before I ask the question. Foreshadowing, I'm not going to open it to answer it, but I just want you all to think about it. Then I'm going to teach you. So we're going to come back to this. We're not going to ask it right now. What's the direction of angular velocity if viewed from above if an object is going clockwise? So I'm not going to open the question. We're going to come back to this. So I have an object going clockwise. The problem is clockwise isn't a good direction vector. Like if I said draw the clockwise vector, that's like nonsense. Like what the heck? What are you going to draw? Like are you going to draw it there? Or are you going to draw it like over here? Clockwise is not a good vector. We can't draw a clockwise vector. We need a vector that points in a straight line. Up, down, left, right, out of the page, into the page. So basically my question to you all is, how do we decide the direction of something rotating? How do we decide, these are vectors, how do we decide the direction of this? Is it up? If something's going clockwise, do we say it's up? Do we say it's down? Do we say it's out of the page or into the page? We're going to come back to it. But it's something I just want you to kind of think about because, it'll explain why when I teach you the rules for how to do it. If you didn't realize up and down don't make sense because at some points it's going up, at some points it's going down. So we can't use up and down. So how the heck do we decide? I'll teach you in a bit. For now, practice with the math. I just asked that question because I wanted to remind you all direction matters. And I will teach you the direction in a little. All right, piece of gum stuck to a wheel with radius 0.5 meters, travels a quarter of a revolution in 5 seconds. What is the angular velocity? The exact same problem, but instead of what is the arc length, what is the angular velocity? Is it 0.5 seconds inverse, 0.5 pi second inverse, 0.1 pi second inverse, or 2.5 pi second inverse? And to give you all a bit of a hint, I'm scribbling that out. All right, give you all about 15 more seconds. And 5, 4, 3, 2, 1. All right, so what's up with this? Why did I scribble out that radius? Look, I'll make it return so you maybe feel better about it. Why did I scribble that out? It says, what is the angular velocity? What is the equation for angular velocity? What is the definition of angular velocity? How much does my angle change every second? That's the definition. Just like regular velocity. How much does my meters change every second? Replace the word meters with angle. It's how much does my angle change every second? Just like normal velocity is meters per second. This is radians per second. So, what's my angle? Quarter of a circle. We already said it's pi over 2. The time is 5, and now you saw I kind of foreshadowed the answer to this when I made the math mistake before. 0.1 pi. Second inverse. So, notice we did not use the radius anywhere in here. Angular velocity, and this is going to be a trend you're going to see me mention, everything on that wheel is experiencing the same rotation. The rate of change of the angle is same everywhere on it. Every part of that wheel, the angle is changing. Its location's angle is changing by 0.1 pi every second. I don't care where you are on that wheel, this is how much your angle is changing. Notice I didn't say on the left side, the right side, the top, the bottom. I did tell you where the gum was, but it doesn't matter for this problem. For this problem, where you're located does not matter. All that matters is how much your wheel is spinning, and everything on that wheel is spinning at the same rate. If it was not spinning at the same rate, that means the wheel would literally be deforming and stretching and doing awful things and eventually breaking. All right. The natural follow-up. Why did I give you radius? There we go. Same problem. What's the velocity of the gun? And this is where the words matter. Angular velocity, velocity. Angular velocity, velocity. They are two different things. And this is probably the most common thing. Do not mix these up. On the final, they're all going to be there. Angular velocity is not velocity. They mean different things, and it's a very subtle, it's literally one word difference, and it means something drastically different. You know, a green hot dog is way different than a hot dog. I guess it's a type of hot dog, but yeah, I guess that's not a great example, but clearly adding an adjective in front changes the word. What is good old normal velocity? Yeah. Did I not start it? No. My bad. All right, you've had so much time to think, though. Oh, this is a good one. What do y'all call a cow that just had a baby? Decaffeinated. It has no link to caffeine at all, but it's just funny word, I guess. All right, 10 more seconds. And 5, 4, 3, 2, 1. Now, there's two ways to get this answer. The first way is you can find the arc length. So S equals R times theta. You can find the arc length, and then you could divide that by the time. And that works. And distance over time gives you velocity. Makes sense. But this is the exact same thing as saying velocity equals r times omega. These are the exact same expressions. So good to remind yourself of that. So in the last problem, it's convenient. We already found omega. So v is going to equal 0.5. In the last problem, we already found omega, so I'm not going to bother with it again. And if you multiply these two together, you get the velocity. Ta-da, 0.05 pi meters per second. And something of note in this problem, remember, I keep forgetting to mention this, but it's always a skill that you should develop. It's always a skill that should be somewhere in your mind. Does my answer make sense? Does my answer make sense? This is a very low velocity. 0.5 times pi, that's 0.15 meters a second. That is very slow. Let's look at our problem. I have a wheel that rotates a quarter of its revolution in 5 seconds. That is a very slow wheel. So, you all understand a wheel rotating, and you all understand meters per second now. So you can ask yourself those questions to check your work. On the final, you all have 2 hours and 50 minutes for 40 multiple choice questions. So it's basically double the time with less work. You will have time to check these things, and so I encourage you all to do so. Look, if you haven't seen me if you haven't been making mistakes in this course, you've seen me make a lot of mistakes in this course. As a reminder that it happens to everyone. Check your work. No one's going to do it for you, unless you pay someone, I guess. But on the test, you won't have anyone to pay. So, anyway, all right. There's a thing I've been saying. I've said it 3 times now. Derivation: v equals r times omega. So, if v equals r times omega, and s equals r times theta, I'm eventually going to teach you in 2 slides. There is something called angular acceleration. So how am I going to go from angular acceleration to regular acceleration? Multiply it by r. Isn't that nice and easy? Really easy derivation. How do you go from velocity to acceleration? Take the derivative. If you take the derivative of the right side, the r gets pulled to the front. Again, this slide, that just says the things I've already told you, nothing new there. I just want to jump to it. Ta-da, there it is. We'll come back. All right. Calculate the angular velocity of the Earth about its axis. That's my first question to you. And I'm going to scribble out these ones. Notice I've given you absolutely no information. And about its axis, meaning the Earth's central axis. Calculate the angular velocity of the Earth about its axis. You all know what you need to know for this. That's my hint to you. Try it out. See if y'all can set this up. You may be like, but you didn't give me things. You know those things. Just think about it. I guarantee you every single person in this room knows what they need to know to solve this problem. I will prove it to you. If not, I'll be very curious why you don't know it. And that's not me saying anyone here is stupid. That's me saying you all know this. You know what you need to know. You just got to figure out what you need. Find its angular velocity. About its axis, about the Earth's own axis. All right, so there's 2 equations you could think of. You could do v equals r times omega. And you may be like, but I don't know the radius of the Earth and I don't know how fast you're going. That's true. So that's useless. We also just have the simple definition, y'all. Angle over time. That is velocity is meters over second. Angular velocity is angle over second. Same exact idea as normal velocity. And this is where I was saying, you all know this. How much does the Earth rotate in one day? The angle is 2 pi. One full circle. What's the time it takes? 24 times 60. 24 hours in a day. Times 60 minutes in an hour. Times 60 seconds in a minute. And this is where I was saying, all of you know how many hours are in a day and how many minutes are in an hour and so on. And that's it, y'all. It's just angle over time. Now, this is moving at a constant velocity. The Earth is not speeding up or slowing down. We'll start to get the problems where it speeds up and slows down. Not the Earth, but other things. This is a constant velocity. This works for that. If it's not constant, you got to use kinematics equations. All right, so you get 7.3 times 10 to the minus 5 radians per second. It's a small number. Yes, the Earth, we're going to find out that yes, the Earth, relatively spins fast, but the angle doesn't change that much. It takes a lot of seconds for the Earth to spin. But the thing's absolutely massive, so makes sense. All right, follow-up questions. Find the velocity at the equator. Find the velocity at the North Pole. Oh, there's the answer. Oh, no, the answer's not there. But that's fine. I believe you. All right, so really straightforward. How do you go from angular velocity to velocity? Multiply it by r. And this thing hates when I try to write there for some reason. I don't know why it does that. All right. V. There we go. It's accepted that. V equals r times omega. So you just multiply the angular velocity times where you're located. So if you do that at the equator, you get 6.378 times 10 to the 6 times 7.35. Nope, 7.3 times 10 to the minus 5. And you get an answer that's like 400 something. 463, I agree. Fun fact, speed of sound is 343 meters per second. If you are on Earth's equator, you are traveling, and this is going to sound in air quotes, faster than the speed of sound. And you're going to be like, what? But I don't feel that. Like right now, you are traveling like 300 meters per second. Velocity is all relative. All velocity is relative. If you are in a bullet train going 100 miles per hour, you can't tell. If you're in a bullet train, you can take a nap and have no problem, assuming the ride is gentle enough so you don't get jerked, aka accelerated in different directions. Velocity is all relative. Everything around you is going the same velocity. All the air molecules are going the same velocity, so you do not feel it. You don't realize it because velocity is relative. Who cares what your velocity is? It only matters what your velocity is relative to the stuff around you. All right. Now the second one, what's the velocity at the r times omega equals 0 times omega. All right. At the North Pole, your tangential velocity is 0. At the top, you're not spinning, you're not like traveling, if you're at a ball, the top point on a ball isn't moving. If you have a ball that's spinning, Sure, the outside of the ball is doing this, but at the very top of the ball, around the axis, it's just sitting stationary. So spin a ball, see it for yourself. Why is this problem really interesting? This is why they launch rockets in Florida. This is why they launch rockets near the equator. If you want to get things to space, everything is relative, but you actually get this velocity when you launch from the equator. When you get to space, this velocity is useful to you. This velocity is relative to kind of everything else in the solar system. So this is a very useful thing. It costs less fuel. The closer you are to the equator, the less fuel you need to get to orbit. You get free velocity, a lot of free velocity. Yeah?
Why is orange 0?
So at the North Pole, the radius from the North Pole is 0. If you're at the North Pole, it's a good question. So if we draw a picture of this, part A, you're located here. So it's spinning about this axis. So R is the distance here. If you're at the North Pole, R is 0. If you're at the North Pole, you are not, if the ball is spinning, you're not moving. Again, put a dot on the top of a ball and spin it, and you'll see that dot in the top doesn't move. Put a dot on the outside of the ball, and you'll see that dot spin around the ball because it's moving. So, yeah, rockets launch from the equator. The closer you get to the equator, the less fuel you need. And then it becomes a really interesting cost analysis. Is it cost efficient to ship your parts? So, for example, the James Webb Space Telescope, they launched that from, I think, French New Guinea, closer to the equator than Florida is. It was a massive payload. It was worth the cost for them. Most things get launched from Florida or Texas because it's down near the south. Every country does this. Every country that's trying to launch things, they try to launch it as close to the equator as possible. Because I don't care what country you're in, physics is the same. So, it's cool stuff. All right. Now on to angular acceleration. Boom! It's the same thing as regular acceleration, but for an angle. It's how much my angle is. It's how much my angular velocity is changing. Is my ball spinning faster and faster and faster, or is my ball spinning less and less and less? It is not the same as spinning. It's whether you're spinning faster or spinning slower. Just like acceleration. Acceleration isn't whether you're moving, it's whether you're getting faster or slower. It's the same as acceleration, but instead of distance, instead of linear, it's rotational. Is my thing spinning faster and faster and faster, or spinning slower and slower and slower? Same exact idea. And remember, how do you go from angular to linear? Multiply by r. Super nice. So units, just chuck another second on the bottom. Just like meters per second squared, this is radians per second squared. But radians is a made up, doesn't count as a unit, so. So yes, if you understand acceleration and velocity, you will understand angular acceleration and angular velocity. Same exact ideas. Just replace meters with radians. All right, so let's practice, Here's an equation for the angular position. Theta as a function of time. Here is my theta as a function of time, 4t cubed. Find the angular acceleration function. All right, we'll go for like 30 more seconds. All right, and 5, 4, 3, 2, 1. So again, if you understand position and acceleration, you understand angular position and angular acceleration. How do you go from position to acceleration? You take the second derivative of it. How do you go from theta to angle? You take the second derivative. So take the derivative once. And that's going to give me omega. So that's going to be 12t squared. How do you go from omega, angular velocity, to alpha? You just take the derivative again. It's the rate of change. That's all a derivative is. Derivative is a rate of change. In this case, with respect to time. There it is. Very nice. Okay. And now we get to circle back, which all the circle buttons. We get to circle back to direction. I've been teaching you what the variables are. Now I got to teach you the direction of them. Linear motion is very straightforward. If something's moving to the right, what's the direction of velocity? To the right. If something's located, if my origin's there, or let's say the origin's over there to the left of me, what's my position? It's pointed to the right. Left. Pointed left. I do want to remind you acceleration. If something's moving to the right and it's slowing down, what's the direction of angular, or what's the direction of acceleration? If I'm moving to the right and I'm slowing down, what's the direction of acceleration? To the left, because you're slowing down. Great. All that's straightforward. Like hopefully at this point that's straightforward. Here's the problem. Let's go back to this problem that was way in the past, all of, how many minutes ago? 20? Where are you at? There it is. What's the direction of angular velocity if viewed from above, if it's going clockwise? We can't just say up, down, left, right. Because on the right side of it, you're moving down. On the bottom of it, you're moving to the left. On the left side, you're moving up. Up, down, left, right changes. So that's a problem. We need a vector that doesn't change no matter where you're going. So they did something called the right-hand rule. They said, you know what? Let's find a vector that's kind of doesn't matter where you're located. It works. Doesn't matter how you draw as long as it's clockwise. And it's called the right-hand rule. Why is it the right hand instead of the left hand? I don't know. It's probably because the predominant number of people are right-handed, so that's just the one that was convenient. Who knows? Very simple rule. Very, very, very simple rule. Take your hand, curl your fingers in the direction of the rotation. Your thumb is in the direction of the angular velocity. That's it. Super easy. Curl your hand in the direction that it's rotating. Thumb points in the direction of angular velocity. If it's going, in this case, looking from above, it's going counterclockwise, points up. If it was going the other way, point down. Done. So we choose one that's kind of out or in. And reminder to you all, this is not how you find acceleration. Acceleration is not based on the way you're going. It's if you're speeding up, acceleration is the same direction as the velocity. If you're speeding up, acceleration is the same direction as velocity. If I'm going to the right and I'm speeding up, I'm accelerating to the right. If I'm going to the right and I'm slowing down, acceleration is in the negative direction. So, we're going to practice this. We're going to first practice finding angular velocity, and then I'll give you some scenarios and you'll find angular acceleration. All right? Let's do it. Nope, not that one. That's going to make your life not happy. All right, there we go. Don't worry, we'll do the unhappy one later. A piece of gum is stuck to a tire, it's getting faster and faster. If the wheel is spinning clockwise, so the piece of gum is on the right side, what is the direction of the angular velocities? I even gave you a picture. You'll often see me give you a picture because describing the direction is always a fun time. We generally do things from above. It's kind of a common phrase. Is it down, up, out of the page, or into the page? Page here means the board. Page means the board. Whenever, if I say on the test, I'll usually use like page. Into the page, out of the page, it means your sheet of paper.
How do you choose which direction to curl your hand?
Whichever way it's going.
Is the way your fingers go.
Yep, whichever, that's a great question. How do you choose which way to curl it? Whichever way it's going. If it's going clockwise, make your fingers go clockwise. If it's going counterclockwise, make them go counterclockwise. And line it up with my board. Make sure your hand matches the board. Do your fingers curl counterclockwise? Are they curling the same direction as this arrow? Alright, I will show you all this one before I close it. Here's my board, here's my hand. I need my fingers to curl the direction of it. They curl the direction of the arrow. Behold, my fingers follow the arrow. That's all you gotta do. Make your fingers follow the arrow. It is impossible for me to, I can't do that. It's impossible for me to just make your fingers look like the arrow. That's the key here. So you curl it, people online have no idea what I'm saying, or they can't see it. Aren't you glad just wait till physics 2, you're gonna have 3 right-hand rules. Yeah, I have 2 right-hand rules to teach you in this class. In physics 2, you're gonna have 3 of them. Make sure we show up in person to those classes because, gosh, understanding, you need to see the visual. Great! Hopefully you got the answer. I'll close it out in 3, 2, 1. All right, if you curl your fingers, your thumb points into the page. Now, let me show you all why it's called the right-hand rule. If you use your left hand, you get the exact wrong answer. Your hand point close. I mean, just do it with both your hands. The thumbs point different directions. And if you do the wrong hand, you get the wrong answer. The same will be true in physics 2. In physics 2, you'll use your right hand for protons and current. You use your left hand for electrons, if you want to, or just use right hand and swap it. All right. Oops, I skipped a what the? Weird. I cannot erase that. Oh, it's gone. Spooky. All right. Do not take what I just wrote down as the answer. It may or may not be. You may be like, oh, we just gave the answer to the next one. If you want to believe that, you can. Next problem, same problem. A tire is spinning, but it is spinning slower and slower. It is rotating clockwise. It is spinning, but it's slowing down. What is the direction of the angular acceleration? The angular acceleration. Not angular velocity. Last problem, angular velocity. This problem, angular acceleration. Always make certain you know what you're solving for. And I'll open the question. So then just think of normal velocity. If my velocity is going to the right and I'm slowing down, which way is acceleration? And if I'm slowing down, which way is my acceleration? It does go the opposite way. That's good, but that's the connection. All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. And I forgot to show you all some notation that you don't need for my class, but it's good to know for physics too. So, first question. You cannot just jump to angular acceleration. You first have to ask yourself, what is the direction of the velocity? So, what is the direction of velocity? We figured this out. The velocity is into the page. Omega is into the page, and this is where I'm going to show you all some notation. Look, drawing an arrow into the page is almost impossible here. Like, what am I going to draw? If I draw an arrow like that, that looks like an arrow up to the right. So, we use the following notation, X and dots. An X is into page, and a dot is out of page. If you ever see a dot as a vector, that means out of page. You will see this in physics too. I am mentioning it now, not because you need it for my class, but because all of you have to take physics too, and better to see it now than then. I'm going to give you all a trick for this. This is the way I remember this. I don't have this like memorized per se. Remember, learning is all about connecting something to something you already understand. Helps you remember things. So, what is something that most of us are familiar with? A bow and arrow. And you'll be like, what the heck? Like, why is he saying this? Alright, a bow and arrow. An arrow that shoots from a bow has feathers at the back, and it has a tip at the front. If you see an arrow getting shot into the board, what do you see? The feathers at the back. They make a nice X shape. If an arrow is going into the board, you see the feathers at the back, it makes a nice X shape. If an arrow is getting shot out of the board, what do you see? The tip of it. Just a dot. Super easy way to remember that. That's how I remember it. Anywho, omega is into the page. So omega, we could draw like omega is an X. Whatever, something like that. That's kind of silly, but... Now, that tells you nothing about angular acceleration. What tells you? I mean, nothing by itself. It's spinning slower and slower. If omega is into the page, how do I slow that down? I make an angular acceleration out of the page. It cancels it out. It decreases the value. It slows it down. There you go. All right. Fantastic. We got directions. We got equations. All right. Now I'm going to hit you all with an unpleasant one, which is going to, I say unpleasant. I'm going to hit you with a question I could have asked on test 1. So, this question I'm about to show you, I could have given you on test 1. We'll get to it. I skipped it before. A piece of gum is stuck to a tire that is spinning faster and faster. If the wheel is spinning clockwise, and if the piece of gum is on the right side, what is the direction of the net acceleration? Notice it's just the word acceleration. It has nothing to do with angular acceleration. It's just acceleration, but I also use the word net, which means you have to add up one or more things. You can't add stuff if there's one thing. There's no point in me telling you net acceleration if there's only one of them. So, what accelerations are affecting this? And I can ask you this on test 1. This question, everything you need to answer this could have been given on test 1, or if you really want test 2. So no right-hand rule here. What accelerations are happening here? So no angular acceleration. Don't worry about angular acceleration. This doesn't ask about angular acceleration. It just says net acceleration. Acceleration by itself. I'll give you all like 25 more seconds. All right. And we'll close this out in 5, 4, 3, 2, 1. All right. So, something is going in a circle. If ever something is going in a circle, remember something should be at the back of your mind. Centripetal acceleration is one of those. It's always there if you're going in a circle. Then what's the other acceleration? It is spinning faster and faster. So not only, sure, yes, it has a tangential velocity. That velocity is getting larger and larger because it's spinning faster and faster. So you also have a tangential acceleration. That point is speeding up downwards and it's speeding up towards the inside. And the result of all of that, remember how you add vectors. So if I have two vectors and I want to add them, tip to tail. Draw one vector. Draw the other vector, and the final result is from tip to tail. There you go. So it is down to the left. So again, this could have been on test 1, and that acceleration in this case is speeding up, so it's getting a tangential, and it's always got centripetal down and to the left. It's a good one. There was a question like this actually on the problem set for, I think, test 1. That if you worked through them all, you probably didn't have a fun time with it. But if you did it then, it benefited you now. All right. Now, because of time, I'm going to just jump to this problem that we're going to solve, and it'll be the last thing we talk about today. So I'm going to come back to this slide. But this part down here, we're going to find it in a problem. So boom, just skip through all those. I'm just going to give you all the answers here so you can reference them. It's spinning clockwise. Direction of angular velocity is out of page. So remember I told you all there is some problems where I might just give you the answer. I'm putting it there so you can check it for yourself. That one's out of page. That one is into page. So they're here. They're good practice. Check them out. All right, great. Remember, talked about this. Take all the kinematics equations. Replace them with the angular variables. Wherever x is, put theta. Wherever v is, put omega. Wherever a is, put alpha. And they all work the same. It's very, very nice. This one I will ask next class. All right. This is the one that I will hopefully be able to solve in the next 12 minutes, 11 minutes. It's got a bunch of steps. It's a good problem. This is number 8 in the next problem set. So this next problem set 3, is the last thing that we're going to cover. I will not be able to teach you enough to solve all of problem set 3. As we get through next Thursday, I'll kind of tell you all you need to know up to this point. And then I'll cross out the rest or something. But I'm leaving all the problems there in case you want to practice them on your own or whatever. They'll exist. This is number 8. It is not number 1. It's not number 2. And you may be like, obviously it's not. Number 8 means it's going to be complex. There's going to be a lot of steps here. If it was number 1 or 2, it's very straightforward. If you can solve this problem, you understand not only the angular variables, you also understand their relationship to the linear variables. That's why I like this problem. This problem has it all. It has you using angular kinematics, and it has you using translational. And so basically, I will work through it, but this is a fantastic one to kind of practice and make certain you understand, because it's got it all, which is why we're going to do it. So, a bicycle wheel with radius of 0.3 meters rotates from rest to 3 revolutions per second in 5 seconds. What is the magnitude of the acceleration vector at the edge of the wheel at 0.5 seconds? What a simple wording of the problem. You got a wheel, it's spinning, it's getting faster, and then at 0.5 seconds, what's the acceleration vector at a specific spot? Not the direction, just the value. All right, so we're going to first start with our givens. And again, I'm just going to kind of work through this one, but it's one you definitely want to work through on your own. What's given? Let's do the easy ones first. We got a radius, 0.3 meters. That's my radius. We got a time. Now we have 2 different times here. We have a time that tells us like it goes from rest to 3 revolutions in 5 seconds. So I guess you could call that like t total. I don't know. Call it what you want. I'm going to call it t total. And then we have a second time that specifically is used to find our answer. So that'll actually get chucked into step 2. What is my velocity? Or what is my acceleration vector at this other time? Great. Okay, so what's given here? So many things that we might have to change some stuff. We see at rest. Immediately, that tells you a lot of things. That tells you your initial velocity is 0. And it tells you that my angular velocity is 0. I don't know why it does this, so I'm just going to exit this. It did this to me last time. I need change this, duplicate this, go to the stream, fix the things. All right, great. We know our initial angular velocity is 0 radians per second. 3 revolutions per second is not my final angular velocity. Revolutions per second is the wrong units. The units for angular velocity are radians per second. And so it's a very small, so this revolutions per second, I both have and haven't taught you this. This is actually something called frequency. Frequency. You don't need to know its frequency, actually. You don't even need to know the name of it. Doesn't matter. It doesn't show up in a single equation that you need to use, but I'm mentioning it because it's just kind of maybe useful for your future life or whatever. You don't need it for my class. Great frequency. So what? I want angular velocity. How do I go from revolutions per second to radians per second? Yeah, you just multiply it by 2. How many radians are in 1 revolution? 2 pi. So, you all just discovered, if you saw that, you discovered this equation. Omega equals 2 pi f. Again, you didn't need to know this equation if you just realize, and I'll kind of write it out here, 3 revolutions per second, if I multiply that by how many radians are there per revolution? 2 pi. Every revolution has 2 pi radians. Oh, look, the revolutions cancel. And I get that my final velocity is 6 radians per second. Angular velocity. You know, it's another thing we can do. We can find the final velocity. If I have my angular velocity, how do I find my final velocity? Equals r times omega f. Remember, just multiply it by r. How do you go from angular to regular? Multiply it by r. So what is my final velocity? It is 0.3 times 6 pi, which equals 1.8 pi. You could plug that in and actually put the number, but I'll just leave it for that because I don't want to plug it in yet. Look at all these things we have. So many things. What are we solving for? We are solving for net acceleration. Net acceleration. And remember, if we draw a picture, this is the problem. The reason I'm doing this problem immediately after the last one. We have tangential acceleration. We have centripetal acceleration. If you have 2 vectors that are perpendicular to each other, how do you add them? You square them and add them together. Remember, if you have an x component and a y component, two perpendicular components, how do you get the net? Square one plus the square of the other equals the final. And we're specifically finding this at t equals 0.5 seconds. That matters. That matters. Okay. And you look at this and you're like, what am I going to do? How do? The same way you solve any complex problem. One piece at a time. That's how you approach anything complex in life. If it looks complicated, break it into pieces. How am I going to find a tangential acceleration? Tangential acceleration is just normal acceleration. We are assuming a constant acceleration in this problem because I've never given you a problem where the acceleration wasn't constant. So how do you find acceleration? If only we had some nice kinematics equations that gave me the relationship between velocities and acceleration. Remember, y'all, VF equals V naught plus AT. If you know the final velocity, you know the initial velocity, you know the time, you plug it in and you get what you need. So the final velocity, we know that, 1.8 pi. We know the initial velocity, and we know the time. We're going to use the total time because this final velocity is specifically at 5 seconds. So then you just solve, and we get that A is 1.8 pi divided by 5. And, it's on here, so I'm just going to take that answer. 1.13 meters per second squared. Look at that. We got one of the terms. Halfway done. You take something that looks gross and you break it into pieces. One of the worst things you can do when solving a problem is to freeze up and just stop trying. That's pretty much, if you freeze up and stop trying, you're definitely not going to get anywhere. Try to find a piece you can do, and then go from there, and then go from there. Yeah? Yeah, that's a great question. Why did I use 5 seconds instead of 0.5? Because this final velocity corresponded to its velocity at the 5 seconds. This final velocity was the velocity at 5 seconds, not at 0.5 seconds. But this acceleration is a constant. This thing is accelerating at a constant rate. I could have specified that problem. It probably would have been a bit better. This is a constant acceleration. I've never given you all a problem where the acceleration was changing. You can't do it. You'd have to have more information, and I haven't taught you how to do that either. All right, great. Now centripetal acceleration. How do I do this one? You all know how to get at centripetal acceleration. There's literally only one equation for it. Tangential velocity squared divided by r. So then, you just have to figure out the tangential velocity at 0.5 seconds. You got to figure out the velocity at 5 seconds. There's 2 ways to do this. One, just use the equation I just used. Just replace time with 0.5 seconds. That's one way. So I'm going to copy all this, and I think I'm just barely going to squeak this in, and maybe I'll get the final, show you all the final answer tomorrow. But I think I can just squeak in this last minute what I need to show you all to finally solve this problem. So how do you get tangential velocity? I'm going to just V final equals V initial plus AT. V final equals 0 plus the acceleration that we just found times 0.5. That's one way to solve this. If you want another way to solve this, you can use a really handy relationship, which is that Vt equals omega times r. So if you can find the angular velocity at that time, you can also use this expression. You'd have to find the angular velocity, which involves a bit more steps. But we'll show you that next time. We're kind of out of time here. So next class, I'll show you we can find angular acceleration, and we can solve this another way. There's 2 ways to solve this problem. Basically, all in linear variables and all in tangential.